Hi everyone, today I'm going to be teaching lesson 8.3, Factors Affecting Solubility. So yesterday's lesson was all about like dissolves like, and this is going to be looking at what other factors can determine what makes something more soluble or less soluble. Here's this little cartoon to help you out. Just get in the mood for chemistry. Okay, so today's aim is 8.3, how do temperature and pressure affect solubility? I'm going to try to do a little demo here over video and the lesson, and then homework is homework 12. So the question of the day is about the lesson from yesterday, which would be most soluble in water and why? So we've got three options: calcium hydroxide, water, and CH4, methane. So when we're thinking most soluble, we're thinking like dissolves like. So water is polar. So the thing that would dissolve best in water would be something else polar or something else, something that's ionic. So this first one, calcium hydroxide, is ionic. So that would be the best choice. Water in water is actually not a solution. That would just be a pure substance. And CH4, if you can picture that, that's a non-polar molecule. So it would not dissolve well in something polar like water. The best option is A, calcium hydroxide, because it's ionic. All right, taking a look back at homework 11, for number 2, you're drawing magnesium chloride being dissolved in water. So here's the water molecules all surrounding the ions. And magnesium is positive, so the negative oxygen side of the water is closest to the Mg, and chloride is a negative ion, so the positive end of the water molecule, the H side, is closest to the negative chlorine. For number 5, you're thinking whether each pair, solute-solvent pair, would make a good solution, and if so, what's the attraction that makes it be a solution? So this first pair, we've got carbon tetrachloride, and that's nonpolar, and the solvent CH4 is also nonpolar. So yes, they would work well together. The attraction that holds them together are weak intermolecular forces. These two are both polar, so yes, that would make a great solution as well, and the attraction would be dipole-dipole. And same with this last one. These are both polar, so they're great at dissolving each other, dipole-dipole. For number 6, you're thinking, would each solute do a better job dissolving in water, which is polar, or oil, which is nonpolar? So this first one, SiH4, is nonpolar, so it would dissolve better in oil, which is also nonpolar. Whereas calcium chloride would dissolve better in water because it's an ionic compound. This one's also ionic, so it would do better in water. And this one is polar, so it would do better in water. All right, so here's our demo today. Do raisins sink or float in water? So here's my soda water, and I'll add a raisin and we'll see what you think. Ah, it sinks. I'll add a few more. Or do they float? And if you can't see this very well, you can also look it up on YouTube. It's a really common experiment. Or you can try it at home. All you need is soda water and raisins. I'm going to try to hold it up a little closer so you guys can see. You can't really see. Okay. What happens is the raisins get surrounded in bubbles. Oh, there goes one up to the surface. Then the bubbles all pop, and then the raisin sinks. And then at the bottom, it gets covered in bubbles, and then they fly back up again, and then all the bubbles pop, and they sink. So this demo kind of helps us see how carbon dioxide, the bubbles, really don't want to stay in the water, right? Why not? Well, carbon dioxide, what do you think? Is it polar, nonpolar, or ionic? That's right, nonpolar. And you know that water is polar. So carbon dioxide does not dissolve well in water. It takes a lot of effort to get it to be in water, and it escapes really easily. So the little bubbles form like a life jacket around the raisin. It pulls it up to the top, then they pop and escape, and then the raisin falls back down. We'll just leave these little dancing raisins here for the rest of our lesson. All right, so our aim is 8.3. How do temperature and pressure affect solubility? And a nice quote there for you. All right, so let's look at temperature. So as temperature increases, you can mess with the solubility of something, whether it's nonpolar, polar, ionic. Maybe it dissolves easily, maybe it doesn't. You can still change how well it dissolves using temperature. So the result, though, is going to be different if you have a solid or a liquid or a gas. So say you have a solid in a liquid. You can think about cooking soup. If you want all those solids to kind of start dissolving in the soup, you're going to heat it up, right? Because solids become more soluble in liquids. Now that is not true for gases. This picture is of a stream, and streams carry a lot of dissolved oxygen, O2, oxygen gas in them. And that's really important because everything that's alive in the stream is breathing that oxygen. We know that warm streams are really bad for salmon, and when we've had heat waves in Oregon, a lot of salmon have died. That's because when you heat up a gas, it becomes less soluble in a liquid. So while solids become more soluble, gases become less soluble. Come on, PowerPoint, work. Please work. Okay, not working. Sorry, guys. Yay. Okay, there we go. Gases become less soluble in liquids. So the example would be dissolved oxygen in streams. All right, so what happens when you open a can of soda, like I just did? You hear that sound, right? That's the sound of all the gases escaping. So now we're going to look at the effect of pressure on solubility. You can also mess with solubility using pressure. So as pressure increases, it doesn't affect solids because they're just not really affected by pressure. They already have a shape and size, so squeezing them or squishing them doesn't affect them. But gases become more soluble. So in a can of soda, if you pressurize the soda, that holds the gases in a little bit better. As soon as you release the pressure by opening it, the gases are going to escape. And this is a picture of that. So you increase the pressure, it's like you're squishing those gases into the liquid. They become more soluble. Now, we've got a reference table that shows us how solubility is affected by temperature. And these are called solubility curves at standard pressure, which is 1 atmosphere. So you can see on the y-axis here, we have how many grams of solute you can dissolve, excuse me, and then the x-axis is temperature. So like at 25 degrees Celsius, that's room temperature, I can dissolve about 10 grams of this thing, which it looks like is potassium chlorate. Also, it looks like I can dissolve about 10 grams of this thing, which is sulfur dioxide. So this table shows the maximum amount of solute that can be dissolved in 100 grams of water at whatever temperature, at a given temperature. So you can take a look and see which substances increase in solubility with temperature. Or in other words, which ones get more and more and more soluble the higher the temperature. That would be all the ones that are going up. So these guys. Which substances decrease in solubility with temperature? That would be all of these ones. So which ones do you think are solids and which are gases? Well, all the ones circled in red must be solids because they get more and more soluble as you heat up the water. All the gases are the ones circled in orange because it's harder and harder to get them to be in the liquid the more you heat them up. All right, here's another way to read this graph, which is specifically how many grams of NaNO3, sodium nitrate, could be dissolved in 100 grams of water that was at 10 degrees Celsius. How about at 80 degrees Celsius? So here we find NaNO3. Let's go down until it intersects with, here's 10 degrees Celsius. So it looks like at 10 degrees Celsius, you can dissolve about 80 grams of sodium nitrate. Versus at 80 degrees Celsius, here's 80 degrees Celsius, woo, you can dissolve a lot more of that salt in the liquid. You can dissolve like 146-ish grams of sodium nitrate at that temperature. Cool. All right, now let's imagine if you put 60 grams of potassium chloride, KCl, in 100 grams of water at 80 degrees Celsius, what do you think would happen? So let's find our curve. Here's potassium chloride, KCl. The water's at 80 degrees Celsius, quite hot. And we're putting in 60 grams of potassium chloride. Well, it looks like we can only dissolve at that temperature about 52 grams, but we put in 60 grams of potassium chloride. So that means 52 grams could dissolve, and then about 8 grams, or the rest, would all sink to the bottom of the cup or the beaker, and they'd just kind of be sitting there on the bottom and they will have not dissolved. Cool. So these are a couple examples for you to work on. That would be to work on with people at your table, but you can work on them on your own. So example 1, how many grams of potassium nitrate can be dissolved in 100 grams of water at 40 degrees Celsius? Looking at your table, of course, like your reference table. How many grams of HCl can be dissolved in 100 grams of water at 90 degrees Celsius? And then a slightly sneaky question, how many grams of HCl can be dissolved in 200 grams of water at 90 degrees Celsius? And then example 3, could you make a solution of 20 grams of HCl dissolved in 100 grams of water at 80 degrees Celsius? So you can pause the video, try to figure those out, and then come back for the answers. All right, so example 1 is about 64 grams. 2 is about 46 grams. The sneaky question would be twice that, because you have twice as much water, 200 grams of water instead of 100 grams of water like on the graph. And then example 3, yes, you could make that solution and you'd have room to spare. You could add some more grams too, and it would still be a solution. That would still work. So that's it for this lesson, guys. Thanks so much for tuning in, and be sure to let me know if you have questions. The homework for tonight is homework number 12.